So gentlemen, we will continue with the second presentation of Dr. Sevinger. The name is Passive Optical Splitters. I think time is yours.
Thank you very much. Thank you very much. So, in my second presentation today, I would like to tell you something about passive optical splitters. I have prepared some kind of outline. I will talk about what are actually optical splitters, principal splitting characteristics, applications, which splitting approaches are used today. I will skip fabrication because it's the same like for WG, so I think we will save the time. Maybe I will say a few words about influence of fabrication tolerances, and then I will show you some optical splitter optimization. So up to now, up to this point, it's the theory, and the last point is what are our efforts, what we reached in the optimization of optical splitters. So optical splitters are similar like AWGs are passive optical components. It means they work without applying any external source. What it means, we couple the light into input waveguides, something happens inside, and at the output signal, output waveguides, we will get our characteristics. Students sometimes mix optical splitter with optical demultiplexers. They look similar. They have input waveguide, then we have the device, and then we have n output waveguides. And the same is for the optical demultiplexers. So what is the difference? I was talking today about optical demultiplexers. We couple different wavelengths into input waveguide. Inside they will be demultiplexed according to wavelengths, and in each output waveguide we will get a different wavelength. In the optical splitter we use just one wavelength. We couple just one wavelength into optical splitter, and at the output waveguides we will get a split signal of the same wavelength. So on this slide you can see once again what I was talking about. We have one optical signal of wavelength lambda 1. We couple it inside into the input waveguide, and at the output we will get, in this case, 4 signals of the same wavelength. And this is so-called splitting characteristics of this optical splitter. Similarly to AWGs, the number of output waveguides is 2, 4, 8, 16, and so on. What you see here, the typical pitch between 2 output waveguides is usually 127 or 250. The same you can see on this transmission, on these splitting characteristics. We have 4 very nicely separated peaks, separated in the distance of 127, and here we have again the losses. We measure the losses in each output waveguide. So before I will talk about approaches, I would like to again explain the characteristics, because when we don't understand what it is about, what we got, so we cannot talk about any optimization. So what do we see? Point A is the highest highest peak in our splitting characteristics, the best one. Point B is the lowest one, and of course the difference between those two is this so-called non-uniformity, what I was talking about before. Then we have the highest peak in background crosstalk, but usually we calculate it as an average value of this noise that you see here. When we design optical splitters, what do we expect and what would we like to reach? First of all, we want to have a very low background noise. It means very high value of Bx. People sometimes mix it. Very high isolation or very good isolation mean a very high background noise, very low background noise, I'm sorry, must have a very high value of this parameter. Then what we would like to reach, no losses, of course. No possible, I will explain why. And then, of course, we would like our designed optical splitters to split signal equally. It means to have all signals the same height it means zero non-uniformity. And of course, chip size is a very important parameter. I will talk about that later. So let me say maybe a few words about insertion loss, that's wrong, that is insertion loss uniformity parameter, that is missing one word. No, wrong, that's right, insertion loss parameter. So when we split one optical signal in two signals, we would like to split it 50-50%, it means we will already get 3 dB losses, so we will never be able to reach actually zero losses. And splitting one signal into 4, we will get already the best possibility 6 losses. By 8 it's 9, by 16 it's 12, and so on and so on. This is one example of 1/32 splitting characteristics, and here is always the detailed view of these peaks. And you see the best possibility is minus 50 dB, but usually it's worse because we have some losses, coupling losses. Where can we use optical splitters? Optical splitters we can use everywhere where we need to split one optical signal into n. Optical signals, they can be used on the chip, so we don't have to count additional coupling losses. And the main application is in in the passive optical networks in fiber to the premises, or mainly fiber to the home applications, where this technique allows several customers to share the same connection, bringing high-speed networking and television into the residences using fiber optical cables. One example of this is Austrian telecom provider A1. This provider bought, I think 2 years ago, from Cisco the whole optical system. They paid 500,000 euros for that, and now they are installing all these cables, optical cables. So it's a new technique. How can we split one optical signal into n signals? There are two main approaches, so-called wide branches and MMI coupler. MMI stands for multimode interference coupler. This is the design, or just the picture. This is the simulation, and here again, design and the simulation. And I will now explain what these approaches. I will start with wide branches. Somewhere I read that this is the simplest possibility to split one optical signal into two signals, and it is mostly used. You see it here, it's really simple because you just have one waveguide and you split it into two waveguides and you get a splitting. When you want to split signal into more optical signals, you use the cascade of 1/2 splitters. So you see this is 1/2, and then again 1/2 and 1/2 and so on. So the question is it really so simple? And if not, why is it used in the, mostly used in the optical data transmission? So on this slide, I would like to show you some first designs we made. This is a simple 1/4 wide branch splitter. As I mentioned, we used the same technology, low index contrast silica technology. So we had a core, cross-section of the core 6 × 6 microns to fit into single mode fibers, and these are refractive images taken from the foundry. Here you can see already the simulation. What you can see in the branching points, you have some splitting, you have some scattering of the light. You can see it also here. What you cannot see here also, during the passing these branches, there is some scattering of the light. Here is the typical splitting characteristics, and again the detailed view of insertion loss and insertion loss uniformity. We reached, I would say, so quite good splitting characteristics, and from those we calculated 3 splitting parameters: insertion loss uniformity, insertion loss, and background crosstalk. This is already optimized design. How did we do it? We use OptiWay software tool. In this tool, you can find 3 predefined forms of white branches. You can see it here, and we tested all 3, and the best result we achieved for so-called Aspen Arcus waveguides to describe just the form. So we use this one in our design. The width of this splitter is constant. I mean constant, you cannot play much with it, you don't have much freedom because you have the pitch between 2 waveguides is 127 times 3 because you have 3 spaces between 4 waveguides, and it is 341 microns. The length was optimized. So first we optimized 1/2 and this is 1/4. So we optimized the length to get the best splitting characteristics. And as you see, already 1/4 wide branch splitter reach nearly 2 centimeters. So it's quite big, quite long, let's say. This 1/4 wide branch splitter was used to design 1/8. So we used 2 1/4 splitters and we connected them together. And then we used 2 1/8 and connected together, and so on until 1/32 and 1/64 wide branch splitters. On this slide you can see design and also the simulation on 1/64 wide branch splitter design. This is our 1/4 splitter, and here we have the splitting characteristics again with the detail. And what is astonishing that is this splitter is more than 30 centimeters long. So it's really long, and this is the first disadvantage of wide branch optical splitters. They will get really long. Splitting characteristics, background crosstalk minus 42 is okay, but you see insertionless uniformity is the difference between the lowest and highest peak doubled from 1/4. So the more channels splitting channels we are using, the worse we get our splitting parameters. So what was the next step? Next step was to optimize the length of this optical splitter, and as I mentioned, there is no much freedom. You just have to squeeze it. So to make it shorter, you cannot play much with this design. And we really did it, and we optimized it. We reduced the size to nearly 1/3 of the original length. And here you can see background crosstalk didn't change much, but insertionless uniformity, the difference between the lowest and highest peak, nearly doubled again. So we've got a high deterioration of splitting parameters. So this is probably, we analyzed these results, and it was probably the wrong way, but only one way how to reduce the size. So here you can see the comparison. This is the original one, and this is the reduced sized one, and you see these parameters. So these are the main disadvantages of using this approach. The splitters will be large or long, let's say long. They have high non-uniformity, particularly for high channel splitting, and of course they have much higher losses. So my question is, why are they the mostly used in the photonics? Does anybody know? They are polarization and wavelength independent. And that is the main advantage why they are used. Because we design one splitter and we can use it at any wavelength range. So we save the money simply. So this is a 16 channel, the measurement of the 16 channel, 1/16 channel wideband splitter from NSJ. What you see here, this is the wavelength range. This is this wavelength range. I showed this picture already in my first presentation. And what you see here, they measured the power in each splitter, changing the wavelengths, and you see it didn't change much. just here. This is this big where we have the water molecules in the fibers, so we have always some additional losses. So this is the main advantage. We did some simulation. Let's say my master student, Linda Koller, she investigated the wide band splitters, and you really can see at each wavelength you can get very nice splitting. So you always can recognize your 16 split peaks. And also they are polarization independent. This is a TE polarization, and this is a TM polarization. And if you compare those three parameters, they are nearly identical. So let me conclude once again. Wide band splitters are wavelength independent and polarization independent, but on the other hand, they have very high asymmetric splitting ratio, causing high non-uniformity of the split power over the old output channels, and they have high insertion losses, large footprint, and they are also sensitive to fabrication imperfection. Why? You see, the whole splitter consists of many thin waveguides, so any technological imperfection will particularly, I would say, at these points, imagine that we have here 1 6 micron waveguide, and then technologically we split it not equally into two. So here we have 6 and here we have 5, and we get immediately asymmetric splitting at one point. And if you have the more such points, like for example here, you will accumulate this error, so you will have a very high non-uniformity. A multi-mode interference coupler is another approach you can use. You can see it here. What we have here is input waveguide, and then we have a very large multi-mode interference coupler. So what happens here? We couple the light from this side into the single mode waveguide, and in the large MMI section, this light becomes divergent, and we excite the higher modes. And these higher modes interfere with each other, and they create such a beautiful, from my side as a woman, very nice multi-mode interference pattern. What you see here, the red is the power, and the green, there is a nothing. So probably from this you already can guess how we do the splitting. You see there are, for example, here two power maxima. So when we cut the multi-mode coupler at this length, so what we get 1/2 splitting. When we cut it here, we get 1/3 splitting. So only the thing is we have to calculate how long should be our splitter, or how long should be this coupler. So and this is what I was talking about. Here we have 1/8 fourth splitting point. So when we design our splitter, we design it just as short as it is shown here, and we will get at the end 8/4 splitting. And what we have to do, we have to add output waveguides, those catch the light. So here, how to design such a splitter? There are a couple of parameters. We have the input waveguide, multi-mode section, and output waveguides. And if we know how many outputs we would like to have, we know the designed, or the wavelengths for which we design this splitter. We can choose the width of this coupler, and from those parameters, we know, of course, the technology. We can calculate the length of our coupler. The length of our coupler. From my experience, I have to say, you always need some feedback from the technology. So you have to make some tuning in the length. So it's not exactly a calculate and it's okay. So some microns you have to try to shift, and you will to find the appropriate length to get the best splitting. But it works very well. It really works very well. So here, this is what I was talking about, and here you can see this is the design and this is the simulation. You see already the difference. We have quite a lot of scattered light out of the multi-mode section. We have also some coupling problems from this copper into the waveguides, and you can see it very nicely here. So we have much higher background crosstalk. But we have insertion loss is quite similar to wide range, but we have insertion loss uniformity 0.12, and this is nearly 10 times less. We had 1.3 for wide range, and here we have 0.12. So we have much, our opti-split signals are all nearly the same. And this is what I will show you here. Here is a comparison. So this is first one. Design, the same waveguide structure, the simulation, and this is what I was talking about. You can get much better splitting and much better insertion loss uniformity. So, so advantages of this splitter are, I didn't say, can you see probably here? Yes. Look at the length of this 4-channel and of this 4-channel. The length of this MMI is less than half. So they are much smaller, these MMI splitters. They have much better splitting properties than uniformity, but they have higher crosstalk and higher background crosstalk. And now is the question, why we don't use these MMI splitters more in the data transmission than the wide branches. I have already switched it, so you probably could read it. They are wavelength and polarization dependent. So you design MMI for one wavelength, and it works for very short wavelength range. So, question? No? Okay. So this is again the simulation of my student for T and TM, and you already see that there are already for 1x4 MMI splitter, there are already some they don't correlate with each other, so they are not the same. Some difference, I'm sorry, in the values, and of course, if you have a higher number of output channels, it will get worse. So here it looks maybe difficult to understand, but I will explain. So here with these simulations, I would like to show you why they are wavelength dependent. Our splitter was designed for these wavelengths, 1.55. So we cut the length of the MMI section appropriately here, where we have 4 maxima, and we added output waveguides. But when we change the wavelengths, we go to the shorter wavelengths. What happened with our multi-mode pattern? It stretches. Look, it stretches. Here is it exactly at those 4, and here it goes this direction. You can see it. And here we are already by 5-fold splitting. So they really work only in this small range. Is it clear? Yes. And here we are going in the different direction. So the longer wavelengths, and of course, they shrink. They just shrink. So we are already out of this 4-fold splitting. So they are really designed for one wavelength, and they work only in a very short wavelength range. So what I want to say is this: we have to design for each application new, also fabricate a new MMI splitter. So this is the conclusion about MMI splitters. As I said, they have large splitting number. So when we split in 1/64, we get much better splitting parameters. They have low losses or lower losses. They have much smaller chip size. They have stable splitting ratio, so it doesn't vary very much. And they have very good fabrication tolerance. Do you know why? We have students here, and I like always asking questions. What do you think why? Why they are so intolerant to so they don't feel if you have small irregularities in the technology? The splitting appears in the very large multiple interference coupler. So if the width, what is the width of this? 400 microns on the lens is, I cannot read it very well, I think it's about 9,000, so half micron plus minus, the light doesn't feel it. So they are really intolerant, they don't feel this, so this is also advantage of this splitter. Disadvantage, wavelength and polarization dependent. They are also used, so it's not that we don't use them, but they are used they are designed for a special application. You build up the optical system and you are using very narrow range of wavelengths. So, and you need your splitter, so you design the splitter, maybe my splitter much shorter, much better for this wavelength range, and it works, and it really works. So this is just a conclusion or comparison. This is what I was talking about, parameters. Maybe the most important is we try to calculate the chip size, and you see how fast is growing the chip size of wide range splitters. So this was the theoretical part, and now I would like to show you some results that my students reached. First of all, I was talking about 1/64 optical wide-band splitter, and I was talking about the problem when we optimize the lens, we deteriorate strongly the splitting parameters. So we were thinking about this, so also how can we, what should be the problem and how can we solve it? And we notice, and we know it, that in the 6x6 waveguide, we don't have only single mode. Or also the first mode is already present. It's not strong, but it's here. And if you think your signal is a superposition of course, you get at this wide range points, you get already there not equal. How to explain? They don't split equally because you don't have the very nice Gaussian shape. And what we did, very simple, we just reduced the size of the waveguide. You wouldn't believe what happened here. So we reduced the lens to 1/3, from more than 30 to, or nearly 32 centimeter to 12. It's a very nice lens from 1/64 splitter. This is 6x6. This is 5.5 times 5.5. And what we got better results. Our non-uniformity reduced from 2.67 to below 2 dB, and we also improved insertion loss. Insertion loss, I think, was very similar, but we improved insertion loss uniformity, and we were able to reduce the length to 1/3 of the original lens. Another result I would like to show is also the work of my another master student, Linda Kohler. She was thinking about how to optimize the used wide range, and she noticed that there is a lot of scattered light at the curvature of this wide range, so she created completely new design. I'm not talking about that because we are preparing a patent on it, so just for you the information, and you'll see already here that this noise here, this everything is eliminated. And so what we did, this is 1/32 wide-band splitter, this is original 6x6, a waveguide cross-section, and just simply changing from here to here, we could reduce background crosstalk by nearly 9 dB. It's a lot. It's a lot. And also, we achieved improvement of the non-uniformity by 1.7 and insertion loss improvement by 1.69. Linda Kohler started this idea, and by another student, Katarina Butcher, she optimized it, this design, and she did a lot of simulation, a lot of tests, simulating tests, And she got for her master thesis award as the master thesis of the year in mechatronics, just in mechatronics in Austria. But I think it is. I was very proud of her because it's not easy to get such a good result. She is now my PhD student. So, last optimization I would like to show you is one of my earlier works. When I started with design of passive optical components, I started with the splitters, and then I moved to AWGs. It will not take long. So this is the design. This is the structure. Again, so that's important. What you see here is 1/8 white MMI splitter. And because it's a low refractive index contrast, we have a lot of scattering here. Also, the separation of the maxima is not really clear, and we have, as I mentioned, we have quite a lot of scattering out of the waveguides when we couple the light into the output waveguides. And so I was trying to optimize it, and I designed simple exponential taper, and I put it between the input waveguide and between multimode section. And let's have a look what happens with the multimode interference pattern. This is the original, and this is the new. Again, this is the original, and this is the new. And now I will go step by step what everything was changed. First of all, we minimized or eliminated the scattering here. The next point are these, I call them eyes. So these are the maxima, and these are the empty eyes here. And look here, and look here. The separation was much better. I will show you once again the detail view. It is not only the separation was better, but you see the eyes, the open eyes are much longer. Once again, short, longer. What does it mean? I was able to increase the operating wavelength range, more than double, more than twice. So, and another thing, what I reached, this look here and look here. So I eliminated. Not completely, but I reduce the scattering out of the waveguides. So, and this is the field distribution at the end of the coupler. You see, even MMIs has a very low non-uniformity. There is still non-uniformity, and we have a high background crosstalk. And this is with using exponential taper. They are nearly identical, high. And this is what I'm talking about. This is a reduction of this noise or background crosstalk. So last slide looks complicated. It's not. I will explain. So what happened here? I designed the splitter and I simulated it in the wide wavelength range. You can see it here. So and what you see here is I calculated for each wavelength. I mean, for each set of wavelengths, I calculated uniformity or not uniformity. This is the conventional one. So this is my open eye. Here I have the multiplexing. Splitting. Here I have the splitting. So I have always about 0.2 dB difference between highest and lowest peak. And when I use the exponential taper, what happened? I have got a wider range, so I can use it for more. And at this designed operating wavelengths, I reached insertion loss uniformity 0.027. So they are nearly, let's say, equal. Then here you can see the same wavelength range, and here you see insertion loss. This is the conventional one. So when I say my splitter should not have insertion loss worse than 10.5 and 6, I choose 10.6. So this is this one. So in this operating wavelength range can work the conventional splitter. And when I used the exponential taper, I reduced the losses here. So I looked for the combination of both. Here we have still very good losses. What I did, I said, okay, when conventional is 0.2, so I can allow my optimized splitter to have 0.2. That was my upper range, wavelength range. And here I looked for a correction between, or correlation between those two. Anyway, the result is I have more than doubled the operating wavelength range of this splitter, and it covers the whole C-band. So this is the last one. Thank you that you have had energy.
Thank you very much for your, I think, very interesting presentation. And please go ahead with your questions.
Okay. I have several questions, but just one. And could you please show me the MMI pattern? Yeah. For example, in this case, could you please comment on the phase difference between the output ports?
Oh, that's a good question, because these results are 10 years old. I don't remember. I'm sorry. Then I moved to AWS. I can check at home, but it's a long time.
Okay, thanks.
I'm sorry.
Any other question, please? Professor.
Can you say me what modeling software you used for the MMI?
This was OptiWave. I like OptiWave. We had Apollo Photonics, if you know. They do not exist anymore. But I have
photonic design?
For passive optical components. And I think this one is, this is OptiWave, I think. We use both. We use Apollo Photonics is much faster. But I don't have the results here. I have to say, if I compare the measurement and the simulation, OptiWave, I get much, let's say, realistic results from OptiWave. So now I'm using OptiWave, PPM
I
simulation.
have a second, if possible.
Go ahead.
You show on my slide that there is a patent
Yes.
for the curve. Who are the patent keepers?
I was working 8 years for optical company called Photon Technologies. They are situated in Bregenz. And at that time I didn't write any paper. We were just, of course, preparing the patents. I have from that time, I think 6 or 7 patents. So it doesn't belong to me.
Any other questions?
Okay, can I? I have several questions. I'm sorry for that, guys.
But we have a time because it was planned for 1.5 hours.
I'm sorry. In wide branches, wide branch splitter, why do design in three dimensions?
We did everything. This is also, all designs were done for 2D simulations. I didn't show any measurements because.
Okay, it's possible to do that in 3 and achieve small.
I didn't do it in 3D because it takes a time, and it's enough to do it in 2D.
Okay.
It takes a time, and you saw in AWGs, but as I mentioned, I started with splitters, and I moved to AWGs, and I don't have any results, any measured results from the splitters. Actually, I should not have any from AWGs, but because I designed all of them, so of course I kept the results. So it's enough 2D.
Okay.
It's enough.
Another question: why use square waveguides in this? It's better to build it in circles for optical fibers or not?
How do you want to do it technologically?
Oh, I don't know.
Okay.
I don't know that.
Okay. You know, I showed when I was talking about AWGs, you start with silicon wafer. Then you grow off your lower cladding, and then you deposit your core.
Okay.
The core. This is 6 micrometer high, and then you have to create a waveguide. How do you create a circle waveguide? When you use dry etching, so you can do.
Okay, the last one. In AWGs, it's possible to make it with space channeling, which is not linear, which is, I don't know,
I know what you mean. So I will not have one channel spacing.
Yeah.
With our new software, yes.
Yeah. Okay.
You say what you want, and we know how to do it.
Okay. Nice. Thank you.
Any other questions? Maybe I will have one. Oh,
Okay. May I
no,
have?
Professor.
May I ask you a stupid question?
No question.
Yeah, your
I'm not sure if I can answer.
Your topic was on splitters, but I am interested in couplers.
Mhm.
So if we input lights from the light side,
From
in
here.
this case, why can't we obtain power combiner
In the middle.
at the output?
You will get it, if you start here,
Mm.
you will have it exactly get on the opposite side, your maximum.
Okay,
Just-
but we can.
It doesn't matter what you, doesn't matter. It depends what you want. Let me come back to the beginning, not beginning, to the theory. So this is exactly,
Yeah.
just a moment, one more. This
Yeah.
one.
Yeah.
So you see when you start, you have here a maximum. So
Mhm.
you have very nice interference pattern, and it
Mm.
ends again. And if you prolong your coupler, you will get exactly the same one. So
Mm.
when you start here and your coupler is long enough, what you get, you will get output of
But
this
if
maximum.
we start from the, for example, two splitter points.
Oh,
I mean,
You start here, I guess.
we input from here. But it's not. Okay, yeah.
It's not.
So you answered your question?
Yeah.
You reply yourself.
I see.
Well, did you try sometimes, I don't know if you have this idea, to compare the diffusion technologies for splitters and couplers? Because they use slightly different technique, changing of the energy of the modes and
No,
wrap it together and fuse together. So
no, I have no.
maybe this will be very interesting to
Yeah.
compare with your results,
Mhm.
with this different type of preparation of the coupler.
Polished is too.
Oh, any other questions? If not, thank you one more time.